Okay, so here's a truss problem. We're asked to find all the forces in the bars. And it's at a point in the course where we now know about zero force members, method of joints, and method of sections. So we're going to mix them all together and try to use them all if we can. We've talked about some strategies in the past, and I'll reiterate it here. So the first thing we want to do just to get started is we'll find our reactions. And then I suggest that we look for simple method of joints that we can do quickly. And as we've talked about before, A would be a good place to start. There's only two unknowns. D would be another good place to start. Also, we'll inspect the truss for any zero force members. We've talked about it before too, but I think I see one that we could get in there very quickly. And then once we've done all those, we probably can look for some sections along the way that'll help us get these members out in the more interior sections of the truss. Okay? So let's go ahead and see if we can solve the problem. So I'll assume that I have a reaction at E, call it EY, and then also at A, which is a pin, we'll have an AY and an AX. And I'll go ahead and do those reactions for the whole truss. So what should we start with first?
Moment of A.
Yeah, that's a good idea. So I'll sum moments at A. Assume right-hand rule for my sign convention. All the forces applied to the truss are going to create what sign on the moment about A? Positive or negative? Negative. So I'll just take them in order. So I've got 6 kips times a moment arm of 20 minus 6 kips times a moment arm of 40 minus 3 kips times a moment arm of 60. And then EY is creating positive moment with a moment arm of 60.
EY is 0.3.
What is it again?
0.3.
0.3 what? Just 0.3? 3 or 0.3? No, it's not 0.3.
You said 9?
It should be 9.
Did they get it? I don't know how to do it.
Let's see, it should be 3, 4, 2, 6. What'd you get?
I got it for AY or EY?
EY.
I think it's 9. Yeah.
What? 9?
I got 9 kills for EY, 6 kills for A.
Okay, 9 it is. I think 9 seems reasonable. Well, I mean, it doesn't have to seem reasonable. What does the equation tell us it is? Does it tell us 9?
It's 9.
Okay. And then if I assume up for my sign convention when I'm summing forces in the Y direction, so I have AY up plus EY and then all those other ones down. Minus 6, minus 6, minus 3. Looks like AY is 6, right? You guys get that? And then we can finish this off. Some forces in the X direction. All I have is AX. So that's 0. Okay? Let me put a little break here and box this off so stay out of the way. So let's apply the strategy we discussed earlier. Let's start at A. Why not? So I'll come over here and we'll do a method of joint or joints at A. So here's my joint. I have AY acting up with a value of 6 kips. And I'll assume a tension force in AG and a tension force in AB. And what's the slope of this guy? Well, I've got 1, 2, 3 divisions. So in this direction, it looks like it goes up 10 feet to 20. So it's like 1 to 2. Does that make sense? So let's go ahead and see what we can get. So we can get AB in one equation. It's the only one with a y component, so we'll start there. We'll sum forces in the y direction. What's the y component of AB? It looks like it's going to be 1 over the square root of 5, right? Acting up. And what else? We have the 6 kip force acting up. So we should be able to find the force in AB. What is it? 13.4. That seems reasonable. It should be negative. Oh, I messed up. Let me see if I can squeeze my negative sign in there. Sorry about that. I tried to jam it in that corner. I shouldn't have done that. Everybody see that? I'm sorry. That looks like B4 too, doesn't it? I messed that up pretty good. So that's 13.4. I'll try to do a better job as we move forward. So now we'll sum forces in the x direction. We have the force in AG positive plus the horizontal component of AB, which should be 2 over the square root of 5. And that's force AB. So when you plug that in there, you should get 12. And that will come out positive. So I'm going to go back to my structure over here and mark off that I now have AB and AG. Now, for similar reasons why we attacked A, we can also go over here and try our luck at D. So let's do that. Oh, joint D. So here's my joint at D. I have an applied force of 3 kips, and then I'll have my assumed forces in tension for the force in DE and the force in CD. And I can also find my slope. What's the same as it was at AB, so it's going to be a 1 to 2. Now CD is the only one with an x component, so let's start there first. So if I assume to the right is positive and I sum forces in the x, what do I get? I would get 2 over the square root of 5. That's the component of CD, and that's it. So looks like CD is going to be 0. And then now when I sum forces in the y direction, make sure they're in equilibrium. I've got my force acting down, force DE, and I've got the load acting down, 3 kips, and that's it. So that's a pretty easy equation to solve. So the force in DE is minus 3 kips. So I'll go ahead and kind of tick off those. Let's see if we've got any zero force members left in the bag. So let's look at the remaining nodes, B, C, G, and F. Remember the first requirement for a zero force member is that what? No force applied at the joint. Well, that eliminates B and C automatically, so don't even look at it. So now we're down to G and F. Now, case 1 is 2 elements connected at a node with no load. There's no case 1s that I see there. Case 2 was 3 elements connected, with 2 being collinear. And I think G qualifies for that. So with that being true, that says that the force in BG has to be 0. So I'm going to come down here and write that the force in BG is equal to 0. And I'll write in that I'm getting that by inspection. That's a zero force member. And I'll go ahead and mark it off. So that leaves me with this 3 here in a section, and then this vertical and 2 here. We'll have to decide how best to handle that. But I think it's going to be pretty advantageous to us now to go ahead and make a cut here, and probably for just for simplicity, I'll work the left-hand side, and I should be able to find these 3 forces.
Did you assume that GF is the same as FAG once you realize BG is 0 force?
Yes. That's a good observation. So I'll go ahead and write that AG should equal the force in GF, and we already have AG. So that means that GF is also 12. So that gives us this one.
Why would that be needed?
Why would it be? Well, all it says is that these 2 forces have to be equal and opposite. And we found AG to be positive 12, so this has to also be positive 12. Tension. So if it's tension on this side, it needs to be tension on the other side. Does it make sense that our truss has a bottom chord that's in tension? Yeah. See, all of our loads are kind of gravity-based. They're acting down. So you'd expect all these elements to be in tension, and the non-zero elements up here should probably be in compression. And what do we find AB to be? I know it's hard to see, but it's in compression. And we also found, DE doesn't make it. DE is a unique case, but it's also in compression. So now I'm going to do method of sections. So I'm going to draw a free body diagram of this part of the truss. I have my reactions at A. I know AY is 6 kips. I have a 6 kip applied load at B. And then I'm going to assume tension here. That's the force in GF, but I already know GF, right? And then I have the force in this diagonal element, which is BF. And then I have the force in this upper chord element, which is BC. So 3 equations and 3 unknowns. And I'll go ahead and indicate that just to remind you that we know what this is. So we can use that to our advantage, or we can pick a way to not include it. So if we did make a mistake previously, it wouldn't affect it. So is there some place I can go, and since I'm doing method of sections, find a place to sum a moment to eliminate 2 of the 3 unknowns? Yeah, F would be a good spot, right? So if I continued these lines of actions of the force, you would see that they are concurrent at F. That's a good spot. So I should be able to solve for BC. Where would be another good spot? Is there some place I can go and just get BF? A. If I go to A, BC passes through A, GF passes through A. I'll start with the first one we talked about. So I'll sum moments at F and make sure they're in equilibrium. Now, just like we've talked about before, then what I want to do is I want this force to slide on its line of action until it's right above here, right? And then I'll have a vertical component and a horizontal component. Everybody see that? And around F, the vertical component would create no moment, only the horizontal component would, and the moment arm would be this vertical distance, which is 20 feet. So let's sum moments about F. First, I'll account for my unknown force. And I'll just make sure you remember this is BC. So I need to know the slope. And we've done this work before. So this is going to be 1 vertical to 2 horizontal. So the horizontal component will be 2/5 of FB, and it's going to create positive or negative moment about F. Negative. So it's going to be minus 2/5 square root of 5, sorry, of BC times the moment arm of 20. That accounts for this. And then what kind of moment about F does this create? Positive. And what's its moment arm? 20. And then the reaction, negative moment, and its moment arm is 40. So what is the force in BC? It looks like it's going to be negative. I can't do that calculation in my head, I'm sorry. You guys have to help me out. 3 times the square root of 5? That's just my Rain Man calculator. Anybody playing along? Bueller? Bueller?
-3 to the square root of 5.
That's what I guessed. Is that what you got?
Yes.
What is it?
-3 to the square root of 5.
Thank you. What is the actual numerical value?
-6.71.
-6.71. Anybody else get that? Hopefully, yes. It would be really reassuring to me right now if more than half of you said yes.
Yes.
Thank you for patronizing me, but did you actually make the calculation? All right, I'll just have to assume that's a yes. Okay, now what? We talked earlier, so now we're going to slide down and look at the moment about A and try to find BF. What I suggest you do is imagine BF sliding down here so that we have a horizontal and a vertical component. And which one of those will create moment about A? The vertical, right? Now that slope, let's see what this element's doing. Let's see, it's going 10 to 20. Oh, do you know? It's 1 to 2. We have quite a few of those. So now I'm going to sum moments about A. So summing moments about A. Look at this force. This force here first slid down. I want the vertical component, which would be 1 over the square root of 5. What kind of moment is it creating about A? Positive or negative? Negative. So it would be minus 1 over the square root of 5 times the force in BF. And what's the moment arm? This distance? 40. Okay, that accounts for this guy. I need to account for this force. Is that positive or negative moment about A? Negative. And its moment arm is 20. And of course the reaction passes through A, no moment. So that's not a bad equation to solve. So what's the force in BF? Looks like it's going to be 3 times the square root of 5.
6.71.
And it's going to be negative. Does it make sense that BF is negative? I would have to say yes, but I can't tell you why. We've run out of time for today's class, so I'm going to stop here. I'll go ahead and mark off that we've now found these, and I will quickly circle the ones we're missing, or put an X through it. So I mean this one, and this one, and this one. See that? So probably what I'm going to ask you to do is to finish this for homework. Now this will not be one, I don't think this is going to be a mastering engineering problem. It may. Okay, so I've given you a good head start on this. I may just assign it on paper. It just depends. If it does show up in mastering engineering, all the forces will be different. And you'd have to follow the same strategy and work your way through. So I may just give you this one and ask you to actually do it on the old-fashioned way on paper.
That way we don't use SAP.
Well, you can always use SAP to check your results if you feel comfortable, but I don't want that SAP output. Okay, we won't see SAP 2000 analysis again, except on your report, and then later in the course when we start doing your second project. There's no avenue for you to show your SAP 2000 skills on the exams.
If we do it on paper, would we regurgitate what you have?
That's completely up to you, Mr. McDonald.
Or do we just find these three members?
I think you should work the whole problem. Okay, any other questions?
On a project, do you want